Here is the paradox of running AI agents locally. The software stack with the highest speed benchmarks can be why your workflow stalls out. The standard developer reflex is to look up the highest token per second benchmark, install that specific serving stack, and expect the system to scream. But the moment the underlying silicon changes, that exact same winning software becomes a slow, buggy liability. Same model, same code, entirely different outcome. On a local budget box, success is not about selecting the superior software. It is a matter of explicitly matching the software stack to the specific metal underneath it. I'm Deirdre AI Guy. Today is day 5 of Poor Man's Spark, and we are looking at the human architect's research on the serving layer. A model file on its own does nothing. It is dead data sitting on a disk. The serving layer is the software that loads it into memory, holds it resident, and manages concurrent requests. For a standard chatbot talking to one human, raw token throughput is an acceptable metric. For multi-agent systems, it is useless. Agents operate differently than humans typing prompts. When you build on local hardware, the serving layer is the specific bottleneck that decides whether a multi-agent system feels responsive or perpetually stalled. When serving multi-agent systems, tokens per second is a vanity metric. It misleads developers trying to optimize their workflows. This horizontal bar chart shows the actual system bottleneck, time to first token, or TTFT. The massive initial block is the wait time before the model speaks. The tiny trailing block is the speed of the words themselves. Agents operate sequentially. They make dozens of short tool call requests every minute. On every single one of those calls, the agent pays that massive TTFT latency penalty before a single token of actual work gets done. Multi-agent loops compound this problem by firing multiple tool calls simultaneously. When 3 agents request data at the exact same millisecond, they create an immediate traffic jam at the endpoint. To optimize local agents, you have to abandon speed metrics entirely. You optimize strictly for traffic control and latency management during concurrent requests. The architectural divide between the big 3 stacks comes down to one thing: what they do mechanically when a second request arrives at the exact same time as the first. Think of them as checkout lanes. The cyan lane bundles everyone's groceries into a single smart scan. The violet lane is a strict single file line. The green lane has one incredibly fast cashier, but a constantly growing line of people waiting. Technically, the cyan lane is vLLM. It uses a mechanism called paged attention to dynamically recycle key-value cache memory, allowing it to bundle and execute concurrent requests simultaneously. This is called continuous batching. Contrast vLLM's dynamic continuous batching with Ollama in the violet lane. Ollama uses a rigid FIFO queue, first in, first out. No bundling, just waiting. The benchmark data is clear. At 50 concurrent requests, vLLM scales to roughly 920 tokens per second. Ollama's FIFO queue flatlines near 155 tokens per second. When multiple agents communicate simultaneously, the software's queue architecture overrides the raw speed of its underlying inference engine. If vLLM is so powerful, why does it actually feel slower than Ollama for a single user making a single request? It comes down to overhead. Ollama is a nimble city hatchback, fast cold start, minimal setup, but poor hauling capacity. vLLM is a heavy freight truck. It takes longer to start, but never slows down no matter how much cargo you load. This line chart plots concurrent agents against time to first response, revealing the exact latency crossover point between the 2 stacks. Notice Ollama's single-user dominance. Its lighter Go server posts a rapid 45 millisecond response time, beating vLLM's 82 milliseconds when there is no traffic. But at 50 concurrent users, the architecture breaks. Ollama's P95 latency explodes to an unusable 18.4 seconds. Meanwhile, vLLM maintains a completely flat P99 latency near 80 milliseconds. The most important detail on this chart is the intersection. The performance gap widens sharply at exactly 4 simultaneous requests. The rule is simple: count your concurrent agents before picking a stack. Crossing that 4 request threshold reverses the rules of which stack is actually faster. Everything we just covered relies on an invisible assumption that you are running NVIDIA hardware with CUDA underneath. Stripping away that assumption changes the framework. Dropping an AMD Strix Halo APU into a local box flips the software recommendations you'd normally give a developer. The winner immediately becomes the loser. This logic pathway illustrates the core technical conflict. The AMD Strix Halo reports as the GFX1151 architecture, which exists outside AMD's standard mainstream ROCm compiler support matrix. Because of this compiler mismatch, vLLM on Strix Halo suffers from upstream bugs in its tool call parser. It splits streaming tags and consistently corrupts agent arguments on models like Qwen. For a coding loop, that is a failure point. But a source-built llama.cpp stack bypasses these issues. It executes clean tool calling and delivers 75% faster decode speeds on the exact same AMD APU. Hardware compiler compatibility dictates software viability. The best stack on an NVIDIA GPU is empirically the worst stack on a consumer AMD APU. The final operational hurdle for local agents is surviving idle periods without triggering massive latency penalties when the system wakes up. Think of model management like a restaurant kitchen. You can shut the oven off between orders and make the customer wait for it to reheat, or you pay a continuous utility bill to keep it hot. This diagram shows the difference in residency behavior. vLLM holds models hot by default. Ollama aggressively unloads them to save memory. To fix this in Ollama, you must pass the string Ollama keep alive equals -1. Setting this explicit keep alive flag permanently pins the model weights and the key value cache into memory. The oven never turns off. But this pinning strategy directly consumes the finite VRAM limits we calculated in Day 3 budget math. You are trading system memory for instant availability. Achieving zero latency multi-agent systems requires a permanent tax on system memory. As the architect, you are forced to strictly budget how many models your box can keep warm at once. Zooming out from the technical minutia, we can establish a unified decision rule. There is no single universal winner in local serving. Evaluate specific workloads against specific hardware. On NVIDIA, default to Ollama or llama.cpp for a single agent's lowest TTFT. Upgrade to vLLM for multi-agent loops. But hardware overrides workload. A Strix Halo forces a mandatory pivot to llama.cpp to ensure stable tool calling. Never ask which stack is best. Ask which stack matches this specific workload on this specific silicon this month. Next is Day 6 of the Poor Man's Spark series. We take these serving metrics and finally build the full local agent software stack. If you are building agents on a budget box, especially in AMD Strix Halo, drop a comment with your stack and your latency metrics. I want to see how your hardware is handling the load. The foundational understanding of how agents operate in this series is drawn from the Human Architect's book, AI Agents in Action. However, the specific local hardware benchmarks and AMD Strix Halo findings presented today are brand new, independent research not found in that book. The fastest software on a benchmark can be the slowest software in your actual server rack. Don't pick the winner, pick the match.